Alrighty, so welcome to this next week of material. So we'll be covering 3 sections this week, and then we'll only have 3 sections left. So 16.7 we'll spend all of next week on, and then 16.8 and 9 will be the last week. But anyway, let's get into 16.4. So let's just recall what we talked about the second part of last week. So earlier last week, we talked about this idea of line integrals, and there were 2 kinds of line integrals. There were scalar integrands and vector field integrands. The scalar integrands you want to think of as the mass of a wire, or for example, you have a wire that's made out of aluminum and gold mixtures, and different parts of it have different ratios of the different metals. Aluminum is a lot less dense than gold is, and so basically you have some parts of a wire that are heavier than other parts, and your integrand would capture that difference in density, and doing this line integral would calculate the total mass of such a heterogeneous wire. But then the second kind of line integral that we talked about was the work integrals for when you have a force vector field given by a vector field big F, and you want to know the work done by the vector field on a particle taking some path c. That's what the second type of line integral calculated for us. And so there was some way where you could calculate that directly. There was when you get your hands on the R of t parametrization for your curve. That's how you would do it directly. But then we started talking about later last week about a shortcut for special vector fields. So for special vector fields, you don't actually have to go through all that process that we talked about in 16.2. Instead, you're allowed to use the fundamental theorem of line integrals, which was a shortcut we learned in 16.3. And so what kind of special vector field are we talking about? We're talking about a vector field that is conservative. And so conservative vector field means that it possesses an anti-gradient. So if you remember, the gradient was an operation that started with a scalar function, little f, and spits out a vector field, gradient f. And so our notation for gradient was that upside down triangle, nabla or del f, del operator, I think it's referred to in the textbook. But anyway, if your vector field is the gradient of something, then the work done by this conservative vector field is the change in the anti-gradient. And so this nomenclature, conservative, comes from physics. Basically, in physics, certain forces respect conservation of energy. So that's where this word conservative is coming from. And so in physics, when you're talking about a conservative force, you're talking about a force that's the gradient of a potential energy function. So in the context of physics language, think about our vector field F as a conservative force. And this scalar function, little f, is the potential energy. And so in physics, I think there's a negative sign that they use, that minus the gradient of potential energy is force generated by that potential energy. But in physics, the sentence you would have learned for this is that the work done by a conservative force is the change in potential energy. So that's something you might have learned back in high school physics. There were other things that we talked about as far as conservative vector fields. Remember, we have this path independence of work done by conservative vector fields. So in physics, that would have been the idea that you learned about, that taking a ramp versus taking the stairs results in the same amount of work. Essentially, all that matters is how much your elevation changes, how much potential energy with respect to gravity that you've gained. And so taking like a 10-foot ramp that's really gradual, you're doing less effort over a longer distance. Remember, work is in some sense force times distance. So if you're taking a longer ramp, you're doing less effort, less force over a longer distance. Whereas if you walk upstairs, you're doing more force over a shorter distance. At the end of the day, there's still the same amount of work. The units of work are always energy units. And so that's a way you can think about some of this stuff. And so, yeah, in physics, not every force is conservative. You can have weirder things happen with regards to friction. Friction is something that depends on both position and velocity. The vector fields we're talking about in this course don't involve velocity ever, but we did talk about last week that it is very special to have an anti-gradient. Then most vector fields don't have anti-gradients. It's not an issue of not knowing the formula. It's even worse. That it's not just that we don't know the formula for it or there isn't a formula. It's just it does not have a potential energy. And so our test that we talked about for conservative vector fields was, if you think about Clairaut's theorem, it's pretty clear that, you know, if P is little fx and Q is little fy, that's what it means for P comma Q to be gradient of little f, then Clairaut's theorem tells you that fxy and fyx are the same, and so if fyx and fxy are the same, qx and py have to be the same. And so it turns out if everything's continuous everywhere in R2, that this statement actually goes both ways. But yeah, think about this partial derivative compatibility condition as a consequence of Clairaut's theorem, or related to Clairaut's theorem. Okay, so anyway, that was what we were talking about last week. So a shortcut for work integrals for special vector fields. So Green's theorem, this next section, is a shortcut for work integrals, but not for special vector fields, but for special curves. So eventually when we sort of build our strategy for the types of approaches for all the different kinds of problems we're talking about this chapter, you know, one of the things is going to be, if it's a work integral, that means f dot dr, look out for conservative vector fields. That's a special property of the vector field. But then the other possibility is a special property of the curve. And so let's talk about that. So the curves we're going to be on the lookout for Green's theorem are going to be what we call closed curves. And so we briefly talked about closed curves last week in the context of conservative vector fields, but this works for any vector field. It doesn't matter. So we're on the main lookout for a closed curve. And so a closed curve is just a way of saying basically a loop of some sort, or a curve that the start and the end points are the same, right? If I look at this curve here, if I think about that single point, I can pick any point, it doesn't matter. But the idea is that it loops back on itself. Like a curve that's not closed is going to look something like this, right? The start and the end points are not the same point. But for a closed curve, looks something like that. And so, okay, what does Green's theorem say? And so it says that this line integral p dx plus q dy, which really is just a different way, remember the notation, you could use f dot dr or p dx plus q dy notation. Remember, think of dr vector as being the vector dx comma dy, so that when you do this dot product, that's exactly what you get. But anyway, if you have a closed curve C and you're doing the work done by P comma Q, that vector field, it turns out that it's equal to the double integral of Qx minus Py. So you take these partial derivatives, you combine them in that sense, and that's the idea. And so your curve is going to have to be counterclockwise. Basically, if it's clockwise oriented, you just multiply by -1, no big deal. I guess I should say I'm leaving out some other sort of assumptions that are needed that we're never going to violate in this course. Essentially, the curves that we're talking about need to be what we call simple curves, as in they don't intersect themselves except, I guess, once you close it. So something like a figure 8 that has a self-intersection is what you would call it. This would not be simple. Things get a little bit screwed up like that, but we're not going to try and confuse you with anything like that. So you have to be simple. And then I guess you can talk about line integrals as long as P and Q are continuous, but this right-hand side only makes sense if P and Q are differentiable. And remember, that's not always true, but for this course, generally, outside of that one day where we talked about limits, we're going to assume that everything's continuous everywhere. And by everything, I mean all derivatives, anything that we could possibly need to talk about. So anyway, the big thing here is closed curve and the fact that we're doing work integrals. That all these other little details, don't worry as much about. Differentiability, simple, all that fun stuff. But big hits are closed and work integral. Okay, and so I guess the next thing I wanted to talk about was why intuitively this is true. And before we get into that, this is where I would ask the class, does this QX minus PY seem familiar at all? So maybe take a little pause here on the video, maybe rewind it a little bit because we did talk about it a little bit today. But hopefully you might find that familiar. So anyway, this QX minus PY is something we've seen before. Basically, it had to do with conservative vector fields. So remember, when we have a conservative vector field, QX equals PY, which of course is just another way of saying QX minus PY equals 0. So this QX minus PY is something we've seen before. It's 0 for conservative vector fields. So we already said last week that if you had a closed curve and a conservative vector field, so if both of these things were special, that the work done was 0. So the physical interpretation of this is the idea that when you're talking about conservative forces, if you end up back right where you started, your net work that you've done is 0. So let's say I go walk up some stairs and walk down the stairs. When I walk upstairs, I'm doing positive work because I'm going against gravity. But when I'm walking down the stairs, I'm doing negative work because I'm going with gravity. So the amount of gravitational potential energy that I gained by walking up the stairs is precisely how much I lost when I walked down the stairs. So the total change in my potential energy, which is equal to the total work that I've done, is equal to 0. Obviously, I'm ignoring the friction of the muscle fibers in my body against each other. That's pretty weird when you start thinking about it, but that's why I guess it does, you are expending energy if I'm just like holding something heavy and I'm not moving it, I'm not doing any displacement. I think there is some weird friction that's happening between our muscle fibers. Let's forget about that, that's too complicated. I'm not talking about the friction with my shoes on the stairs, but if I'm only talking about the force of gravity, I'm not doing any work by walking upstairs and then back downstairs because I'm gaining back the potential energy that I lost when I increased my elevation. So anyway, yeah, this was something we talked about last week. The conservative vector fields, closed curves, the work is 0. So in some sense, what we're doing now is basically Green's is saying that for any vector field, the work that it does on a closed curve somehow depends on how non-conservative it is. That, and this will make a little more sense later on today when we talk about something in the next section, but basically you want to think of as QX minus PY as a quantitative measure of, I guess, like how far off your vector field is from being conservative. So maybe how not conservative F is. So Qx minus Py is 0 when it is conservative. It's non-zero when F is not conservative. And so it makes intuitive sense that the work done on a closed curve is going to depend on how far off your vector field is from being conservative. Because when it is conservative, it's no work. When it's not conservative, it has something to do with how far these partial derivatives are from each other. And we can also kind of make some sense on the positive versus negative idea for this. And so this is something we'll talk a little bit later today about using some different language. But let's just intuitively take a look at a specific situation. So let's say that I have my curve C and it's oriented counterclockwise. And let's say I have my vector field. So how do I want to draw it? Let's say it looks like this, basically. So these red arrows are my vector field F. Okay, and so if you remember last week, you can eyeball the sign of f dot dr by asking yourself, how well do the vectors f and r prime line up? And so notice that in this picture that I just drew, f dotted with dr is positive because f and r prime always make an acute angle. Because remember, f dot dr, the way we actually go to calculate it is we do f dotted with r prime dt and do some integral from a to b. And remember, dot product of vectors that make an acute angle is positive. It's negative if they make an obtuse angle, 0 if they make a right angle. But this picture that I've drawn here, I've sort of indicated that, okay, yeah, the vector field is sort of swirling around counterclockwise, so it looks like I'm always making an acute angle with this counterclockwise curve. So anyway, that's positive for this. And so I claim also that Qx minus Py is positive. So, okay, and we'll practice this. I'll do it, I probably won't do it all that much today, maybe a little bit, but it's on some of the homework and something we'll probably talk about in recitation. So I claim that Qx minus Py is positive. So what you can do when you're looking at the picture of this vector field is just kind of eyeball what these derivatives are doing. So remember, our vector field component functions are p and q, so this vector field I'm looking at is p and q. So Qx is basically asking the question, what happens to q when x increases and y is held constant? And y is held constant. Well, we see that it seems to be positive because q is negative here, right? And q is positive here because q is the vertical component. So when the vector field is, this is confusing. I'm looking at this like it's a mirror. It's going to get reversed later. So anyway, as you're going from left to right, the vectors are pointing less down and more up. It happens here, it happens here as well, that as x increases, the vertical component increases. So q goes from negative to positive, which means that the x partial of q is positive. And then similarly, Py is measuring, what happens to P as Y increases and X is held constant. So as I go up, it looks like P went from positive to negative, right? P is positive because the vector is pointing to the right. P is negative here when it's pointing to the left. So it seems like Py is negative, and so therefore a positive minus a negative is guaranteed to be positive. So, and then when you do the double integral of a positive function, you get a positive answer. So granted, this is not a proof of Green's theorem at all. I'm just kind of, well, at the end of the day, all I showed you was that two things are positive. Not all positive numbers are equal, right? 1 and 3 are not the same. But I'm just trying to give you an intuitive idea that you can eyeball the signs of these partial derivatives and therefore eyeball the sign of this integrand. And it's consistent with this idea that it looks like F and R prime are making acute angles everywhere. So you could do the same thing with if you had clockwise swirling, you could deduce that, yeah, both of these sides of Green's theorem are negative numbers. So intuitive reason why Green's theorem works is the fact that like Qx minus Py measures swirling. That if it's positive, it's counterclockwise swirling. If it's negative, you could draw a similar kind of picture and see that it's clockwise swirling. If it's equal to 0, there'd be none. So anyway, that's just an intuitive idea. Okay, but as far as more details for a rectangle. Okay, so anyway, this, if you're really interested in why precisely these things are true, you can go through this. To be honest, when I teach this during this semester, I don't usually go over this in class. Occasionally people come for office hours and I'll talk about it then. So this might be something you don't want to spend too much time worrying about unless you're really interested in why this ends up being true. So let's take a look at why this would be true for a rectangle. So the book does it for a more general region, which is fine. But I figure let's just do a rectangle because it illustrates what's actually happening magic-wise. And yeah, let's take a look. So anyway, let's say, and hell, let's just make it a little bit easier and assume that the rectangle is, we got 0, 0, we got a comma 0, we got a comma b, and we got 0 comma b. Let's just assume that that's our rectangle. Again, this is going to capture all the big ideas while making it a little bit easier to see than if I just had some general region that was going on. Okay, so anyway, let's see here how I would set this up. So anyway, let's say that we're trying to do the work of F along C. And so for this rectangle, I would have to do the work along each piece separately and then add it all up. So whenever you have corners in your curve like this, you sort of have to split it up. We've done examples like this. So yeah, so I'll just write P comma Q for each of these. Okay. Okay, so how am I going to get these going? Well, I guess piece one, well, they're all line segments, so I just kind of go through like that. I'm going to do piece one is R of t is t. Oh, okay. And so the other thing that I'm going to do for this is I'm going to parameterize this with parameter x. I'm going to call it R of x is x comma 0 for x between 0 and a. So I know that most of the examples we did last week, we used t as our parameter. Doesn't matter what the parameter is named, but I'm just going to use x to make it a little bit easier to see something in a few minutes. So piece one, I'm going to say is x comma 0 for x between 0 and a. And I guess I'll write it like this too. So x equals a to x equals 0 to x equals a. Okay. And so in that case, our prime of x is 1, 0. F, so PQ of R of x, so PQ of, I guess I should write it R of x, is, well, maybe I'll write it F of R of x just because that's the notation we used last week. So F of R of x is P of x0, Q of x0, because notice that y is 0 on this entire first piece. And then finally, F dotted with R prime ends up just being P of x0. So the work done on the first piece is the integral from 0 to a of P of x0 dx. Okay. And then I could do something for the next piece. So for piece 2, I'm going to parameterize in terms of y. So on piece 2, x is equal to a the entire time, but then y is going to start at 0 and go to b. So r prime of y is now 0, 1. F of r of y ends up being p of a comma 0. No, I'm sorry. P of a comma y comma q of a comma y, because I'm just changing x to a and y is still y. And then if I do the dot product of f with r prime, I'm going to get the integral from 0 to b of q of a y dy. And then I'm not going to go through the details because they're very, very similar. But piece 3, it turns out that because piece 3, x is now decreasing, you end up picking up a minus sign, and you end up going to get minus the integral from 0 to a of p of x comma b dx. That, yeah, on piece 3, y is equal to b the whole time. It all works out. That you end up getting that. And then piece 4, you're going to get minus the integral from 0 to b of q of 0 y dy. And let me make sure I did everything right. Looks good. So it looks then like the total work of f dotted with dr is, I'm going to rearrange it like this. It's the integral from 0 to a. Well, okay, I'm not going to do it like that. I'm going to do it as 0 to b q of ay minus q of 0y dy minus 0 to a of p of xb minus p of x0. So I know this is a little weird, but this is just what you get when you start setting these up. And then now here's where the real magic happens. I know from Calc 1 that the change in a function is always the integral of its derivative. So the change in f between two values is the integral of the derivative. And so if you notice, that's sort of what we have going on here. That this is the change in q between the values x equals 0 and x equals a. So this really, by the fundamental theorem of calculus, is the integral from 0 to a of the x derivative of q. Because I've made this change in the first slot. And then I get minus the same thing here. This is the change in p between y equals b and y equals 0. So it's the integral from 0 to b of the y partial of p. And then you sort of put that all together with the fact that these rectangles, you could switch the order of integration without any trouble to get that this really is the double integral over that rectangle R of qx minus py. So don't worry too much about this. The takeaway points is that by thinking about this swirling type picture here, we can convince ourselves that, yeah, okay, when f dot dr is positive, it looks like the double integral is positive. Well, why on earth is there this mismatch between the number of integral symbols and things like that? Well, it turns out it's the good old fundamental theorem of calculus. So that's actually what this entire chapter is about, is different manifestations of the fundamental theorem of calculus. If you remember last week, we called that thing the fundamental theorem of line integrals, and it followed from the fundamental theorem of calculus, and that's still what's going on here. So that's really what I wanted to convince you of. So don't worry too much about all these details. I know that we're using x's and y's as our parameters just for convenience, whereas last week we were using t's as our parameters. Not a big deal, but more details for a rectangle and for all shapes. It turns out it's just the fundamental theorem of calculus is the key step that links these two sides. So it's pretty neat. Okay, but then how are you actually going to deal with this stuff? Let's just do a couple of examples. All right, so calculate this f dot dr line integral over this triangle. Okay. So let's talk about both ways we could approach this. So this could have been something we assigned last week after the first lecture last Monday for the calculate f dot dr integrals. So anyway, if you're thinking about doing this directly, you'd have to split this curve up into C1, C2, C3, or 1, 2, 3, whatever you want to call it. You'd have to do three different parameterizations. So C1, you could parameterize by t comma 0 for t between 0 and 1. If you go through and do the line segment setup for this, you'd have 1 minus t, 2t for t between 0 to 1. And then C3, you'd have 0, 2 minus 2t from t equals 0 to 1. And you'd have to do f of r of t dot r prime of t for each. And that's totally fine. You could do it. But it seems like it's going to be a little bit long and tedious. Instead, with Green's theorem, you could just say, you know what, C is closed. So I'm allowed to use Green's theorem, which says that instead of doing this line integral directly, I can instead do the double integral of qx minus py. So I have to do the double integral of qx is 6x, py is 1, okay, and then as far as doing it, got to be careful with the double integrals. So don't forget all the good stuff we learned about double integrals back when this is not a rectangle, so we have to be careful with our bounds, but without too much trouble, you could see that x is going to go from 0 to 1, y is going to go from 0 to 2 minus 2x, and then you have 6x minus 1, dy dx. So that's 0 to 1. Well, the y antiderivative is 6x minus 1 all times y. So you'll have 6x minus 1 times 2 minus 2x once you do the y antiderivative and plug in. And then from there, it's not very exciting, just a good old Calc 1 integral. And so when you're thinking about the trade-off here, we are dealing with a double integral instead of single integrals, but I'm just doing it once, right? I have one double integral I need to do as opposed to 3 different single integrals if I do it that way. And then in addition, notice that often qx minus py is simpler than p comma q. So that's not always the case. We like to give you questions where it turns out that there's multiple hints that make this the way to go, that you're reducing you have to, instead of setting up 3 different line segments, you just have to set up one double integral region. In addition, you have these terms in q that when you take the x partial, they go away. You have these terms in p that when you take the y partial, they go away. So this vector field would be an example of one such that when qx minus py, when we do that, you get some expression that's simpler than p comma q. But that's the idea. All right, so anyway, then next one. Same idea. So I think I'll save it till, I think Dom and recitation will talk about a little more detail about this counterclockwise versus clockwise. It's not always the best way to describe situations, but for these simple sort of warm-up situations, I think it's our best bet. But anyway, if it's clockwise, then all you're going to do is multiply by -1. So if you think about clockwise swirl versus counterclockwise swirl and how that sort of intuitively changes the situation from when right after I introduced Green's theorem, you'll see that, yeah, if you want the signs to work out properly, if r prime is now in the opposite direction, you're just dotting with the opposite vector, so you're always getting minus what you were getting before. And so that's all you have to end up doing. So close clockwise, you just multiply by -1 right here. Okay, and then so again, you could think about doing this 16.2 direct. That's sort of what I call doing the direct calculation instead of some fancy theorem that allows you to change it to something else. But anyway, yeah, you would have to come up with r of t. So I always like to just stick with cosine and sine. You could maybe multiply one of these by -1 to go the other way around, but not both. I'd have to think about it. But yeah, you can like mess around with that. But the way I would take care of this clockwise is to just go backwards with your t bounds, right? Because cosine t sine t, t is basically your polar angle. So as t increases, you go counterclockwise, which means that as t decreases, you go clockwise. So if you wanted to go clockwise, you could do it like this, and then you would do integral 2 pi to 0 f of r of t dot product r prime of t. And so anyway, that's how you could do that. But instead, let's do Green's theorem. So, okay, with Green's theorem, this is our curve C. We're going to do minus the double integral of qx minus py owing to the clockwise orientation. So minus, well, qx is 2, and then py is 2x squared plus 4. And so after you deal with all these minus signs, it looks like we're getting, and you do that subtraction, you're going to get 2x squared plus 2. So at this stage, that's the new part. The new part of this section is going from this closed curve work integral to a double integral. And once you have the double integral, then you do whatever you would have done for that kind of double integral. So disk, you would have done polar coordinates. Don't forget your extra r factor. And then from there, I'm not going to do it. You guys should do it for practice, but not so bad. So this is where everything's kind of coming together, as you can sort of start seeing that the R of t idea from chapter 13, that's showing up when we talk about line integrals. Through the magic of Green's theorem, certain work line integrals are equal to double integrals, and then all the good old stuff we learned from chapter 15 comes into play for double integrals, whether it's setting them up in polar coordinates or setting them up dy dx with our bottom and top curves. You really have to be comfortable with all this stuff. So sort of why chapter 16 is so difficult, because if you're sort of rusty and not good at any of the earlier topics, you're going to have a hard time when they all show up at once. And so granted, you're probably going to do this way for both of these. I was just showing you what would have been involved if you had to do it the other way. But you're not going to appreciate, because you're not going to appreciate Green's theorem if you don't understand how you would have to do multiple calculations for something like this. Or this is another example when you take these partial derivatives, you get something that's a lot simpler than these 4 terms here. So all kinds of reasons make Green's theorem good to do. But that's about it for Green's theorem. I think the tricky part is going to be combining it with stuff as we keep going on. And yeah, like I said, so Dom will do a couple more examples and maybe talk a little bit more about this clockwise versus counterclockwise idea. But yeah, that's pretty much it for that section, but we're not done. Let's do another section. So 16.5 talks about some stuff called divergence and curl. And so don't freak out. This is not the 141 version of divergence, convergence, divergence of series, which, I don't know, some of you might still be traumatized from. But don't worry, we're not talking about that concept of divergence at all. It's a much easier concept. So let's talk about divergence and curl by first reviewing this idea of the del operator as well as the concept of gradient. So the del operator, it's the vector of partial derivative operators. And so it's the only symbol that's a vector in this course that I don't put an arrow over. I maybe should. It's just, I don't know, can't teach an old dog new tricks. I'm not used to doing that. So anyway, you're just going to have to remember that it's supposed to be a vector. So that's what we call the del operator, or I call it nabla sometimes. Can't remember who taught so long ago. But if you look up, so this is nabla. It's what it's referred to, and it's not a Greek letter, right? So I'm not great at the Greek alphabet, but this is definitely not in the Greek alphabet. It actually comes from the Greek word for harp, and because I guess this kind of looks like a harp, right? Oh, I guess the strings would be going down the other way. I don't know how to draw a harp, but you know, the Guinness symbol. I guess that looks like a harp. I don't know. And so anyway, this was called a harp by, turns out it was Maxwell of the famed Maxwell's equations, the guy who invented most of electromagnetism back in the 19th century. We'll talk a little bit more about his equations later. But anyway, upside down triangle, harp shape, nabla, whatever you want to call it, del operator. Think about it as this vector. And so the gradient was something that we did whose input was a scalar function and whose output was a vector field. And for gradient, we wrote that grad of little f, or nabla f, I don't even know how you pronounce it, is, well, think about it like this. It's, I guess, the opposite order that we usually would have thought about for scalar multiplication, but essentially what you're doing here is like scalar multiplication. Remember, if I'm doing, 2 times a vector a, b, c, that's, you distribute the scalar factor to each component. That's what I mean by it's like scalar multiplication. And that's the idea of gradient. Okay, and so these concepts of divergence and curl are going to be similar to this. And as you might guess, they're going to be like the dot product and like the cross product. So let's do divergence first. The divergence is something whose input is a vector field and whose output is a scalar function. And so we're going to write divergence of f as div f. And okay, well, it's going to be like the dot product. So you do nabla dot f. So again, it's not really a dot product because taking a derivative is not really multiplying numbers together. But so yeah, this is a slight what we would call abusive notation, but it's a nice handy way of remembering what this formula should be. So you do the del operator dot PQR, and you get the scalar function px plus qy plus rz. So don't ever do px comma qy comma rz. That's sort of the half-assed dot product. You're going to be really off on the wrong foot if you think the divergence ends up being a vector. So just make sure that you're getting a scalar function as the output of divergence. So that's what divergence is. It's just a particular combination of partial derivatives of the component functions of your vector field. Before we do an example, I'll spoil the surprise and tell you what curl is. The curl is an operation that starts with a vector field and ends with a vector field. So curl of a vector field, as you might have guessed, is going to be like a cross product. And so we're going to put I, J, K, X partial operator, Y partial operator, Z partial operator, P, Q, R. And then you get this really sort of scary looking thing, what, RY minus QZ, PZ minus RX, and then QX minus PY. So notice, if you think about it, between P, Q, and R, and X, Y, and Z, that's 9 different first partial derivatives that are involved. So P, Q, R, X, Y, Z, 9 first partial derivatives. Notice, divergence involves 3 of them. So P with X, Q with Y, R with Z. Curl involves the other 6. So you have PY and PZ, but no PX. You have QX and QZ, but no QY. You have RX and RY. Ooh, so I think So watch out for those of you watching this video. I hope I wrote that right and maybe got goofed up by a undo. But yeah, it's RY minus QZ, as you can see. All right. So div involves 3, and curl has the other 6. So together, each of the 9 possible first partial derivatives shows up either in curl or in divergence. All right, let's do one. So div f and curl f. So div f is sort of the diagonal one. So P is the first component, X is the first variable, so PX. Q is the second component, Y is the second variable, QY. R is the third component, and Z is the third variable, so RZ, sort of the diagonal ones. And yeah, so the X partial of P is 2XY plus e to the Z. The Y partial of Q is 2Y e to the X plus 2Z. And then the Z partial of R is 3Z squared X plus Y. And so, of course, those parentheses I just put there so you could keep track of which terms were coming from which component derivatives. But of course, remember, we're supposed to get a scalar function, no vector, no nothing. You know, divergence is a scalar, divergence is a scalar. So there we go. And then curl F, as you'll see, it's a little bit more annoying to calculate. I've learned it makes your life easier if you do this bottom row first. So you get enough room. Yeah, so curl, the y partial of R is z minus the z partial of q is 2y. Then the z partial of p is xe to the z minus the x partial of r is z cubed, and then qx minus py is y squared e to the x minus x squared. So curl, you know, but this, again, like I said, this isn't really multiplication, and it's not really a determinant. We are abusing notation, so if you're thinking about, you know, some variables times del y, don't think about it like that. Just take the y partial. So, you know, always think you're taking these 6 partial derivatives and combining them together as such. Okay, so finding divergence of curl, that's something you're just going to have to practice on your own. You're not really going to learn how to do it by watching us do it. So let's talk about why we're talking about it. So what do these things measure? So let's do the 2D case. So again, all these things are functions of x and y, whether or not it's a scalar function or a vector field. All these things are going to change, presumably, throughout your vector field. So it's very possible, let's say that, you know, my vector field F, let's say that over here, it looks like this. Let's say that over here, it looks like this. So again, let's focus on the 2D case where our vector field depends on x and y only, and there's no r function. So r is just 0. That's how you could think of a 2D vector field as a special case of a 3D vector field. So in this situation, div f, it's not too hard to convince yourself, is px plus qy, and then curl f ends up being, and for those of you who are really paying close attention, that third component of curl f was our good old friend qx minus py. You might have thought, wait a second, qx minus py, we've talked about that twice. Is that a coincidence? And the answer, as always, is no. So we'll talk about that in a few minutes, the connection there. But, well, I guess here it is right here. So because r is equal to 0, all the derivatives of r are 0. And because for this 2D vector field, p and q are only functions of x and y, you get a bunch of zeros here. So qx minus py, that thing that turned out not only in our conservative vector field test, but also our Green's theorem, ends up being the only possible non-zero component of the curl of a two-dimensional vector field. So anyway, let's say near this point, our vector field looks like that. And then near this point, our vector field looks like that. Okay, so anyway, you could do the same kind of game with the actual partial derivatives, where you ask yourself, what's happening to P? Well, whatever, let's just do it. If X increases, it looks like P is increasing, right? Because when you're talking about Px, you're like, well, hold Y constant, what happens to P? And so our vectors are pointing to the left for smaller values of X, and then to the right for larger values of X. So Px seems to be positive here. And similarly, it looks like Qy is positive because the vectors are pointing down, then they're pointing up. So this region over here, this is sort of the stereotypical picture of positive divergence. And you could do the same kind of thing near this point to convince yourself that the divergence is a negative value there. So essentially, divergence measures, I guess you could call it like spreading out of your vector field. And so if your vector field arrows are pointing away from each other, they're sort of diverging from each other, which that's why it's called divergence. So it's not that scary 141 sequences series stuff. It's coming from this idea of, are the arrows pointing towards each other or away from each other? So spreading out, or compression, whatever you want to think about it. So spreading out would be positive divergence, compression would be like negative divergence. So intuitively, that's what's going on with divergence. Are your vector field arrows going away from each other or going towards each other? Whereas curl measures swirling. So basically here, this was basically the same picture I showed you when we were talking about Green's theorem a while ago, but this counterclockwise swirl corresponds to a positive value of Qx minus Py. And so curl F is a vector, is directly out of the page, right? Because by the right-hand rule, the z-axis is coming out of the page. So yeah, you could say that for a 2D vector field that exists in the page, curl F is either the zero vector or directly out or into the page. And so counterclockwise swirl corresponds to directly out. Clockwise swirl corresponds to directly in. So again, remember, curl is a vector. So we can't really talk about whether curl is positive or negative. That doesn't make sense. We can talk about whether that third component is positive or negative. And then that tells us whether or not the vector curl F points into or out of the page. And that's the idea. So the 3D case for divergence is the same kind of thing. If your arrows are pointing away, that's positive divergence. For the arrows going together, that's negative divergence. As far as curl goes, you want to think of curl F is the axis around which F swirls. So let's say you have this vector field given by these blue arrows here. So the book should have, I stole this out of the book, as you might have guessed. They should have emphasized that these blue arrows are the vector field F. Then the pink arrow is the vector curl F. Remember, everything is a vector here. F is a vector field, curl F is a vector. And so curl F is the axis. Well, I guess I shouldn't call it the axis. I should say it points along the axis around which F is swirling, the length of it is sort of how much of the swirling there is, and whether it's this way or that way is sort of the right-hand rule. So do your fingers around the swirling direction, your right-hand thumb will do that. And so we'll come back to this in a few minutes. I think you might be surprised. Maybe you're thinking about it right now, but I think you all have a little bit of intuition about this, assuming you've done Physics 212 or any sort of, I don't know, my high school physics was garbage. I don't think I learned about it. Maybe I did too long ago. Anyway, let's talk a little bit more about divergence and curl, and then we'll talk a little bit more about why they're useful. So consequences of Clairaut's theorem. So the first is the curl of any gradient is the zero vector. Okay, let's see why. Well, curl, remember you take your partial derivative operators, put them in the second row, and then my vector field is the gradient of little f. So that means my vector field that I'm taking the curl of is little fx, little fy, little fz. So then I do this cross product. I'm going to get fzy minus fyz. I'm going to get fxz minus fzx, and then fyx minus fxy. And remember, Clairaut's theorem is just the statement that as long as your partial derivatives are continuous, your second partial derivatives are continuous, they have to be equal. So again, we're assuming that everything's nice here. And yeah, so if you're the gradient of something, the curl has to be zero. And so again, we do really need to be a little bit careful with, well, in general, you have to be very careful with statements versus their converses. But it turns out that the reverse is true. So if curl of a vector field is zero, and so this is when it gets weirder. Like in the two-dimensional case, you can say that if this is true on a region without holes and things are continuous, then it's the gradient of something. The concept of no holes needs to be more precisely defined as something called simply connected. Don't want to really get into that. So let's just say if curl f equals 0 and the partials of f are defined, or let's say continuous, because that takes into account defined, on all of R3. And again, every other day of this class, other than limit day, we assume that everything's continuous everywhere. Curl f equals 0, that implies that you have an anti-gradient. Okay, and then similarly, so I guess you could say the test for conservative vector field is the curl 0? And by 0, since curl is a vector, I'm really meaning 0 vector. And so that sort of fills in the gap. That last week we talked about qx equals py as our test for conservative. That is the 2D zero curl situation. But now we've sort of expanded our concept of curl to involve all these other things. And so that's how you would test if a 3D vector field is conservative, is whether the curl is 0. Test for whether an anti-gradient exists. So yeah, conservative is just a different way of saying, does the vector field have an anti-gradient? Does it arise from a potential energy function? Okay, and so then the other consequence of Clairaut's theorem is that the divergence of any curl is 0. And so again, it's just a matter of writing out what this is. So remember, curl was ry minus qz pz minus rx qx minus py. And so when you do this dot product, you'll get ryx minus qzx plus pzy minus rxy plus qxz minus pyz. And notice rxy minus, ryx minus rxy, pzy minus pyz, and then qxz minus qzx equals 0. Same kind of thing, Clairaut's theorem, just the equality of these mixed second partials. Who cares what order you take them in? You get 0. And similarly, that tells us that the test for whether f is equal to curl G, which is just a different way of saying test for if f has an anti-curl, is the divergence of f 0. That the only way you could possibly be the curl of something is if your divergence is 0. So we're not going to worry as much about anti-curls. Anti-gradients are going to be very important for us. We're going to be calculating them a lot. You already have been calculating them a lot. Anti-curl is not something we're going to calculate, but I will mention it in a few minutes. So that's on a couple homework questions. Okay, so then the last thing I want to talk about is just how these ideas of divergence and curl turn up in certain other subjects. So fluid mechanics, if any of you are aerospace engineering majors, I'm sure you'll see this idea. But if the idea in fluid mechanics would be you're studying the velocity field of a fluid. And so there's two different main types of fluids, right? There's, I guess, gas or plasma, which is compressible. And then, of course, there's liquids, which are incompressible. So what's that mean? Liquids change shape, but they can't really change volume, right? It could spread out, but the total volume stays the same. You can't squish water. I mean, okay, you can a little bit, but the incompressible approximation is that the volume of water stays the same. And so if you remember, this idea of expansion versus contraction was a question of divergence. So if you're studying incompressible fluid mechanics, one of the restrictions you have on the velocity vector field is that the divergence of your vector field has to be 0 of your velocity. Whereas for compressible fluid mechanics, so for gas equations, you are allowed to have expansion and contraction of gas, and so you can have non-zero divergence. And so then I guess the other thing that you could do is define something called lowercase omega, which is called the vorticity, is the curl of the fluid velocity. And so if you assume that the vorticity is 0, you have something called irrotational flow, which means that you have existence of a velocity potential. So the word potential is sort of borrowed from the potential energy concept. Remember, vector fields whose curl is 0 have potential energy functions. So in the context of fluid mechanics, that's called potential flow, or you have this existence of some function phi called the velocity potential. And then the other thing too is that basically vorticity is the source of turbulence, that in 2 dimensions, gas flow, or in 2 dimensions, fluid flow can't get too crazy because it turns out that vorticity has to be well behaved in 2 dimensions. But once you get into 3 dimensions, the real world, you can have very complicated, I guess it's called vortex stretching, and your vorticity can initially be small, but eventually get big, and that causes the concept of turbulence, which is why the weather's hard to predict. And so yeah, I guess this stuff, I said aerospace engineers, but I know some of you might be meteorology majors too. I'm sure you'll talk a lot about vorticity as well. So think about tornadoes, hurricanes, swirling. All this stuff is important as far as that kind of stuff goes. Okay, so anyway, last thing I want to talk about was Maxwell's equations for electrostatics, and this will connect some things to Physics 212. So I'm going to pick units where all numbers are 1. You're allowed to do that in math. I'm not trying to do precise equations physics, but I've changed units so that these are going to be simple. So, okay, what do we need for electrostatics? We have something called the electric field. E, we have something called the magnetic field. B, we have something called rho, which we'll call the charge density. And then J will be the current density. The current density is a vector valued density because current has a direction associated with it. Okay, so what are Maxwell's equations then? They're the laws of the land for electrostatics. So basically, we have that the electric field has no curl. The magnetic field has no divergence. Then the divergence of the electric field is the charge density. So there should be some nonsense like 4 pi epsilon naught, where epsilon naught is the permittivity of electric permittivity of space. I've changed units. These aren't meters and kilograms anymore for these units. I've made it so that all those messy constants are now equal to 1 when you combine them together with the units. So yeah, the divergence of the electric field is the charge density, and the curl of the magnetic field is the current density. So you could think about this as saying B is the anti-curl of magnetic field is the anti-curl of current. And this process of doing the anti-curl is the Biot-Savart law. So something you might have learned in physics was, okay, you have your current, you do the Biot-Savart law to help you figure out what's going on with the magnetic field. You're essentially taking the anti-curl. So this is where I want to go back to this slide here. This curl you want to think of as current, and then this vector field you want to think of as B. So if you've taken Physics 212, you do have a little bit of intuition already with regards to this idea of curl. Curl is just the relationship between magnetic field and current. So that's pretty neat. And so then we can even talk about some of those Clairaut's theorem consequences that we had. The fact that the curl of the electric field is 0 tells you that there exists an electric potential. So I'm sure that's something that you've talked about in physics. The fact that the magnetic field has 0 divergence is there exists a vector magnetic potential. I think that's A, or at least that's what Wikipedia says is the standard. Let's see here, vector magnetic potential. I don't feel like maybe that wasn't until Physics 400 where I saw that. Oh, and so I guess physics and fluid mechanics followed the same idea that, at least according to Wikipedia, phi is the standard Greek letter for electric potential, and then A is the vector magnetic potential function. So anyway, Maxwell came up with all this stuff when he was formulating these equations. They were already being used as far as fluid mechanics equations. So all this concept of expansion, compression, swirling, it's all very natural and very important in these fields. And basically this whole chapter, this vector calculus chapter, we're essentially learning all of the various versions of the fundamental theorem of calculus that ended up being very important in the 19th century when Maxwell and Stokes and Kelvin and all these other heavy hitters in the field of physics were figuring out what was going on. And so anyway, that's that. Tomorrow we'll talk more about a new way of talking about surfaces to get ready for evaluating integrals on surfaces, which is going to be pretty tricky. And that's what we'll spend all of next week on. Alrighty, but I will catch you later. Have a good day.